Hi everyone, my name is Bencherif Mokhtar. I'm a PhD student at Mouloud Mamrez University of Tizi Ouzou in Algeria, and I am pleased to present our research on the data-driven optimization of martensitic phase transformation models in 304L steels. Before diving into the specifics of our research, I would like to provide an overview of today's presentation. Starting with the introduction to martensite quantification in austenitic stainless steels. Then we will describe the experimental setup and methods used, such as incremental tensile tests, magnetic measurements, and optimization process. Then we will discuss the different results obtained at all levels. And finally, we will conclude with the list of conclusions. But first, let's begin by framing the motivation behind this work. So, martensitic transformation plays a fundamental role in the mechanical performance of trip steels. In metastable austenitic stainless steels such as 304L steel, strain-induced transformation from austenite to martensite enhances both strength, ductility during deformation. This unique behavior is what gives strip steels their exceptional energy absorption capacity and the resistance to failure under dynamic loading. Stainless steels are widely used across key industries due to their strength, formability, and corrosion resistance, such as aerospace, food industry, automotive, and construction. In all these sectors, controlling martensitic transformation is essential for performance and reliability. This motivates our work on developing predictive, data-driven models to better understand and optimize phase transformation in advanced stainless steels. Conventional methods like X-ray diffraction, electron backscatter diffraction, or even optical metallography, although accurate, are limited by accessibility, cost, and the need of extensive sample preparation. Moreover, these methods are often destructive and poorly suited for real-time or industrial applications. In contrast, magnetic measurement techniques like Barkhausen noise and eddy current techniques offer a promising non-destructive alternative, but these two require robust calibration models to translate magnetic signatures into quantitative martensite fractions. This is where data-driven modeling and AI-based optimization comes in, enabling us to build predictive tools that are both interpretable and practically usable. Moving now to the description of the experimental setups and optimization methods used in this investigation. So, in this research, we employed a mixed method approach combining experimental tensile tests on standardized tensile test specimens and magnetic flux density measurements. So, on the left side of the slide, we have the ASTM A370 standard, which specifies the specimen's geometry in the context of sheet metal plates. The highlighted columns indicate the selected dimensions. On the right side, a 3D representation of the test specimen geometry is depicted. We first performed a series of tensile tests up to complete failure to deduce the main mechanical properties of the material, particularly the displacement which corresponded to failure strain. After that, we were able to identify each displacement corresponding for each increment as shown in the table below. All of the experiments were carried out under quasi-static conditions at a speed of 5 millimeters per minute. Samples were then prepared from the deformed specimens to be analyzed using XRD to get the phase composition variation. The analysis was performed using the parameters listed in the table hereby, and the equation shown here is used to calculate the martensite value fraction based on the intensities corresponding to the alpha prime martensite and to the intensity of the austenite plane. The next part of the experiment was to record the magnetic flux density using the Tesla meter shown on the left figure. These measurements will be then correlated with martensite volume fractions obtained previously from XRD and will form the baseline for the upcoming optimization process. Now, the real challenge is turning those signals into meaningful martensite content. That's where model selection matters. This table summarizes 6 nonlinear models from purely empirical to physically grounded ones. This diversity let us compare both predictive accuracy and how well each model reflects the actual transformation process. To optimize each model, we used 6 algorithms ranging from local to global strategies. This diversity here helps assess not only accuracy but also the robustness of the optimization process. We will now present and discuss some of the main findings of our work. On the left, we have incrementally deformed tensile test specimen going from 20 to 100%, showing the progressive elongation and naked. On the right, we have the magnetic flux density measured by the Tesla meter, which is increasing slowly with strain, indicating the formation of strain-induced martensite, a ferromagnetic phase replacing paramagnetic austenite. This provides a clear quantifiable magnetic signal linked to the transformation. On the phase peaks, flux density, and site. This confirms flux density transforms the experimental predictive models. This shows the martensite fraction as a function of magnetic flux density for all 6 models. Each model was optimized using the same data set and follows a nonlinear saturation trend with a sharp increase beyond the magnetic threshold. This comparison helps assess how each model captures both the growth phase and the saturation behavior of the transformation. This table shows the final optimization results for all 6 models, all calibrated using LMA algorithm for consistency and reliability. The LE model achieved the best predictive performance with the lowest MSE and the highest R-square value. Among the physical models, MA and OC also performed well, both R-square above 96%. In contrast, KM and G showed higher errors and suggesting the trend. Less parameters are listed the replicate. This slide compares much good LE models, physical models like OC and MA performed better than empirical ones like G. These results highlight that the best models combine both accuracy and physical interpretability, which is essential for the reliability of the prediction in material science. And here we have global sensitivity analysis to assess. The results showed that all their profile differ, which affectability. In this slide, we have the residual distributions for the two top models, LE and OC. Overall, LE offers a more consistent residual behavior and may generalize better. And to conclude, we confirm the strong nonlinear link between magnetic flux density and the Martensite volume fraction in 304L steel. The LE model was the most accurate one, but not physically interpretable compared to the OC model. This highlights the trade-off between prediction and the meaning of the parameters. Optimization with physical models gives a balanced, explainable approach to Martensite transformation. And with this, we conclude our presentation. So thank you for your attention.